Hello everyone, welcome back to my channel Maths Classes. So today in this video I am going to start the chapter Tangents and Intersecting Chords, and this is the important chapter for the class 10th ICSE. So let's get started. So basically, what is a tangent? The line which touches a circle at one point. So you can see a circle is there. Now if I draw a line which touches the circle at one point, so this line is known as tangent of a circle. And the point where the circle touches the line, so this point is known as point of contact. So it's clear that the line which touches a circle at only one point is known as tangent of a circle. Now if I draw a line in this way which cuts the circle at 2 points, you can see here this is the first point and this is the second point. So now in this case this line is not a tangent. This line is known as secant of a circle. So now moving to the next theorems which are important and which are based on the tangent. The first theorem is the tangent at any point of a circle and the radius through this point are perpendicular to each other. It simply means that if I draw a radius here and a tangent, so this is the radius and AB is the tangent. So this theorem states that the radius and the tangents are always perpendicular to each other. So here I can write that angle OMB is equals to 90 degree. Because radius and tangents are always perpendicular to each other. Moving to the next theorem, the tangent drawn to a circle from an exterior point are always equal. So here if I draw two tangents, this is the first tangent and this is the second tangent. So you can see here that these two tangents are passing from an exterior point, that is P. This point is A and this point is B. So here you can see PA and PB are the two tangents passing from an exterior point. So here we can say that tangent PA is equals to tangent PB. So whenever the tangents are passing from an exterior point, the two tangents will be always equal. Also we can conclude one more thing. If I join this point, this is the center of the circle O. So OA and OB are the radius of the circle. From the first theorem, we can say that radius and tangents are perpendicular. So this angle is right angle and this angle is also right angle. So now these two angles are left, angle O and angle P. So we can also conclude that angle O, it means angle AOB plus angle APB. The sum of the central angle and the exterior angle is always supplementary. That is, the sum of both the angles is always 180. Also we can conclude one more thing, like if I join this side OP, so from here this angle is angle AOP and this angle is angle BOP. So we can conclude that angle AOP is equals to angle BOP. So these are the important theorems you have to keep in your mind. So please have a look. Now moving to the next theorem. If two circles touch each other, the point of contact lies on the straight line passing through the center. So here you can see when two circles will touch each other, there will be two conditions. The first condition is when two circles touch externally. So here, when two circles touch externally, so in this case, this is the center of the first circle and this is the center of the second circle. So here the point of contact lies here. So if I draw a line from the point of contact. So this point of contact lies on the straight line passing through the center. This is the only statement that if two circles touch each other, you can see two circles touch each other externally, the point of contact lies on the straight line. This point of contact lies on the straight line passing through the center. Now, moving to the next condition where these two circles will touch each other internally. So, in this case, suppose this is the center of the first circle and this is the center of the small circle. So, here the point of contact lies at this point. So, if I draw a line, so this point of contact will lies on the straight line passing through the center. So this is the only theorem, so please have a look. Now, based on the same theorems, we will solve the exercise 18a, question number 1. The radius of a circle is 8 cm. Calculate the length of a tangent drawn to the circle from a point at a distance of 10 cm from its center. So here a circle is given to you and this is the center of the circle and this is the radius. So here this is 8 cm, this is given. Now if I draw a tangent, suppose this is the tangent of the circle. So we need to find the length of a tangent drawn to this circle from a point at a distance of 10 cm from its center. So if I join this line from the center to this tangent, so this line is given to us, that is 10 cm. So this is 10 cm and you have to find the tangent. Tangent means you have to find this side, this line. So here from the first theorem I told you the radius and tangents are always perpendicular to each other. It means this angle is 90 degree. So now in triangle AOM. So now here we solve this sum. So in triangle AOM, by Pythagoras property, that is x square is equals to p square plus b square. So this will be 10 square is equals to 8 square plus am square. 10 square is 100, 8 square is 64 plus am square. So 100 minus 64 will be 36. So the value of am is square root of 36, that is 6 cm. So therefore the tangent of the circle is 6 cm. Clear? Now moving to question number 2. So in this case you can see the figure is given to us already. So here tangent AB is given, that is 15 cm, and AC is given 7.5 cm, and we have to find the radius. So here we have to assume that radius is small r. So again from theorem 1 we can state that this radius and tangents are always perpendicular to each other. So here angle B is 90 degree. So again we can apply the Pythagoras property. So in triangle AOB, so by the Pythagoras property we can write for this right angle, this OA is the hypotenuse. So OA square is equals to OB square plus AB square. The value of OA is r plus 7.5 whole square. OB is given, that is r square, and AB is also given, that is 15 whole square. Now in this case you have to apply the identity, that is a plus b whole square. So this is r square plus 7.5 square plus 2 multiplied by r multiplied by 7.5 is equals to r square plus 15 square is 225. Now this side r square plus, now here 7.5 square is 56.25 and 2 multiplied by 7.5, that is 15r is equals to r square plus 225. Now here you can see this r square and r square cancel out. So this is 15r is equals to 225 minus 56.25. So from here 15R is equals to, so 225 minus 56.25 is 168.75. So the value of R is 168.75 divided by 15. So here your answer will be 11.25 centimeter. So this is the radius of the circle. That is the only thing we have to find out. Moving to question number 3. So in this case we have to prove that tangent QA is equals to tangent QB. So now in this case from theorem 2 we can state that the tangent passing from an exterior point are always equal. So here we can prove it. So since QA and QP are the tangent of the first circle, so we can write here QA is equals to QB, and this is from theorem. So this will be your equation 1. In the similar way, we can say that tangent QB is equals to tangent QP. QB is equals to tangent QB. This is again from theorem. So this will be equation 2. Now if you will compare equation 1 and equation 2, you will see this right hand side QP and the same QP both are equal. So hence from equation 1 and 2 we got QA is equals to QB. So this is the only thing we have to prove. So hence prove. So this is question number 1, question number 2 and question number 3. So please have a look. So now moving to question number 5. Two circles of radius 5 cm and 3 cm are concentric. Calculate the length of a chord of the outer circle which touches the inner circle. So in this case, these two circles are concentric circles. So concentric circles are those circles which have the same center. So in this case, the radius of the bigger circle is given to you, that is 5 cm. So this is 5 cm. And the radius of the small circle is 3 cm. This is 3 cm. So you have to calculate the length of a chord of the outer circle which touches the inner circle. So if I draw a chord here, suppose AB is the chord. So in this case you have to find the length of the chord. So you have to find the value of AB. Question mark. So if I join this is the center of the circle. If I join this is the radius, that is 3 cm. Now if I join this side OB, so OB is the radius of the big circle. This is 5 cm. So again from theorem 1, we can state that radius and tangents are perpendicular. So this angle is right angle. So in triangle OMB, in triangle OMB, again apply the Pythagoras property, that is OB square is equals to OM square plus MB square. Now the value of OB is 5 cm, this is 5 square, OM is 3 square plus MB square. Now 5 square is 25 is equals to 9 plus MB square. So 25 minus 9 is 16. So the value of MB is square root of 16, that is 4 cm. But here you have to find the length of the chord. So in this case the chord is AB. So therefore AB is equals to twice of MB. So the length of the chord will be 8 cm. And this is the answer. Now moving to question number 6. Three circles touch each other externally. A triangle is formed when the center of these circles are joined together. find the radii of the circle if the sides of the triangle are 6 cm, 8 cm and 9 cm. So here you can see 3 circles are given to us and these 3 circles touch each other externally. Suppose this is the center of the first circle, this is O1 and this is O2 and this is O3. So if I join all these 3 center, so this will form a triangle. So here you have to find the radius of the 3 circles joined together. So the sides of the triangles are given to us 6 cm, 8 cm and 9 cm. Suppose this is 9 cm, this is 8 cm and this is 6 cm. So in this case, let the radius of the first circle be R1. Suppose this is R1, radius of the first circle, this is also R1. The radius of the second circle be R2, this is also R2, and the radius of the third circle is R3, so this is also R3. So from this figure we can write that R1 plus R2, this R1 plus R2 value is 9. It's given to us that the side of the triangle is 9 cm. So here easily we can write that R1 plus R2 is equals to 9. This is equation 1. In the similar way, R1 plus R3, this value is 8. So R1 plus R3 is equals to 8, equation 2. And in the similar way, R2 plus R3 value is 6 cm. So R2 plus R3 is 6, equation 3. Now adding equation 1, equation 2 and equation 3, R1 plus R1, this is 2R1, R2 plus R2, this is 2R2 and R3 plus R3 is 2R3. And here 9 plus 8 plus 6, that is 23. So from here we can take 2 as common. So 2R1 plus R2 plus R3 is equals to 23. So therefore R1 plus R2 plus R3 is equals to 23 divided by 2. This is 11.5. So now this is your equation 4. So from equation 4, R1 plus R2 plus R3 value is 11.5. Now from equation 1, the value of R1 plus R2 is 9. So in place of this R1 plus R2, if I write here 9, so we can easily find the value of R3. So from here, the value of R3 is 11.5 minus 9, that is 2.5. So the radius of the third circle is 2.5 cm. Again from equation 2, R1 plus R3 is 8. So here in place of R1 plus R3, if I write 8, so 8 plus R2 is equals to 11.5. The value of R2 is equals to 11.5 minus 8, that is 3.5 centimeter. So this is the radius of the second circle. Now in the similar way, from equation 3, R2 plus R3 value is 6. So now in place of R2 plus R3, if I write 6, so what is left? R1. So R1 plus 6 is equals to 11.5. The value of R1 will be 11.5 minus 6. So answer will be 5.5 centimeter. So therefore, the radius of the first circle is 5.5 centimeter, the radius of the second circle is 3.5 centimeter, and the radius of the third circle is 2.5 centimeter. So please have a look. Now moving to question number 7. If the sides of a quadrilateral ABCD touch a circle, prove that AB plus CD is equals to BC plus AD. So here in this case you can see a quadrilateral ABCD is given to us, and also a circle is given inside this quadrilateral. So we have to prove that AB plus CD, this side AB plus CD is equals to BC plus AD. So let's start proving this. So in this case, let us mark these points as P, this is Q, this is R and this is S. So here can I write AR is equals to AQ? AR is equals to AQ. If you will see it clearly that this is a circle and this AR and AQ are the tangents passing from an exterior point A. So it means like wherever the tangents are passing from an exterior point, the tangents are always equal. This is from theorem. So here in reason we can write from theorem. This is equation 1. In the similar way I can write tangent BR is equals to tangent BS. Tangent BR is equals to tangent BS. This is again from theorem. This is equation 2. Now in the similar way, can I write dP is equals to dQ? Yes, dP is equals to dQ. This is again from theorem. The tangents passing from an exterior point. This is again from theorem. Now this is equation 3, and in the similar way I can write that Cp is equals to Cs. Cp is equals to Cs. This is again from theorem. So now this will be your equation 4. Now in this case you have to add equation 1 plus equation 2 plus equation 3 and equation 4. So if you will add this equation 1 and equation 2, this is AR plus BR. Now from the given figure, if you see AR plus BR, this is the complete side AB. So in place of this AR plus BR, I can write AB plus. Now dP plus Cp. Now again from the given figure, this is dP and this is Cp. So dP plus Cp is the complete side DC. So write here DC. Now equals to, now again AQ plus BS from the given figure. This is AQ and this is BS. Now in this case, if you will add both these values AQ plus BS, you won't get any side. So if you add AQ plus DQ, this is AQ and this is DQ. So AQ plus DQ will gives you the side AD. So I can write here AD plus. In the similar way, BS plus CS. Now here if you will see, this is the side BS and this is CS. So BS plus CS will give you the side BC. So this is the only thing which you have to prove. So hence proved. Or we can write in this way, AB plus CD is equals to BC plus AD. So hence proved. So please have a look. Number 10. In the following figure, if AB is equals to AC, then prove that BQ is equals to CQ. So let's start proving this. So if you will see this figure, this A is the exterior point and AP and AR are the tangents. So here from the theorem, I can write AP is equals to AR. This is from the second theorem that the tangents passing from an exterior point are always equal. So here we can write from theorem, and this is your equation 1. In the similar way, I can write that BP is equals to BQ. Since here B is the exterior point and BP and BQ are the tangents. So therefore we can write BP is equals to BQ. This is again from theorem, and this will be your equation 2. In the similar way, I can write CQ is equals to CR. Since C is the exterior point, so therefore CQ is equals to CR. The same reason from theorem. And this will be your equation 3. Now adding equation 1, equation 2 and equation 3. So here AP plus BP plus CQ is equals to AR plus BQ plus CR. Now if you will see this AP plus BP from the given figure, this is AP and this is BP. So from the given figure, AP plus BP is this complete side AB. So I can write here AB plus CQ is equals to, in the similar way, if you see these two sides, AR plus CR. Now from the given figure, AR plus CR is the complete side AC. So in place of this, I can write AC. Now what is left? BQ. Also from the given part, if you say this AB is equals to AC, this is given to us. So here as AB is equals to AC, so both the things cancel out. So what is left? CQ is equals to BQ, or we can write as BQ is equals to CQ. This is the only thing which you have to prove. So hence proved. So this is question number 10. Now moving to question number 11. The radii of two circles are 6.3 cm and 3.6 cm. State the distance between their center if the first part they touch each other externally and second part they touch each other internally. So in this case, two conditions are given to you. In the first condition, the circles touch externally, and in the second condition, the circles touch each other internally. So here one by one we have to find the distance between their center. So the first part, for this small circle, let's suppose the center of the circle is O, and for this big circle, the center of the circle is O dash. So if I join this line, so in this case you have to find this distance. So the first part, you have to find the value of O dash. Now here from the given part, the radius is given to you, that is 6.3 centimeter. So of course for the big circle, the radius will be 6.3 centimeter. This is the radius of the big circle, and for the small circle, the radius is 3.6 centimeter. This is 3.6 centimeter. So it's very obvious from the given figure that the value of this O dash, it's simply 3.6 plus 6.3. So distance between their center that is O dash is equals to 3.6 plus 6.3, that is 9.9 centimeter. This is the answer. Now moving to the second case, they touch each other internally. So in this case, suppose this is the center of the big circle and this is the center of the small circle. So in this case again you have to find the value of O dash. So again the radius of the big circle is 6.3. This is 6.3 from center to this point, and the radius of the small circle is 3.6, and this is 3.6. So in this case you have to find the distance O dash. So it's very obvious, the radius of the big circle minus the radius of the small circle. So therefore distance between their center is equals to, this is 6.3 minus 3.6, that is 2.7 centimeter. So this is the distance between their center. So this is question number 11. Moving to question number 12. From a point P outside a circle with center O, tangents PA and PB are drawn, prove that angle AOP is equals to angle BOP. So let's start solving the first part. So in the first part you have to prove that angle AOP, this angle AOP is equals to angle BOP. So in this case you will take two triangles, in triangle AOP and in triangle BOP. So in triangle AOP and in triangle BOP. So you have to make these two triangles congruent. So here PA is equals to PB. The first thing, PA is equals to PB. Since P is the exterior point and the tangents passing from an exterior point are always equal, so here the reason you write from theorem. Now the second thing, OA is equals to OB. OA is equals to OB. Since OA and OB are the radius, so here is an equal radius. And the third one, OP is the common side. In both the triangles, if you see, OP is the common side. So here the reason will be common side. So therefore these two triangles are congruent by SSS congruency. So therefore triangle AOP is congruent to triangle BOP by SSS congruency. So if the triangles are congruent, then it means this angle AOP is equals to angle BOP. So therefore angle AOP is equals to angle BOP, and this is by CPCT. Corresponding parts of congruent triangles are always equal. This is the only thing you have to prove in the first part. So hence proved. Moving to the second part. So in this case you have to prove that OP is the perpendicular bisector of the chord AB. So in this case you have to join this AB. So here AB is the chord. So you need to prove that this side OP is the perpendicular bisector of the chord AB. It means you have to prove that this angle, you can name it M. So angle OMA, also angle OMB should be 90 degree. Then only we can say that OP is the perpendicular bisector of the chord AB. So let's start proving this. So for this you need to take two triangles, in triangle AOM and in triangle BOM. So here in triangle AOM and in triangle BOM. So here you need to make these two triangles congruent. So OA is equals to OB, equal radius. Secondly, just now from the first part we got that angle AOP is equals to angle BOP. You can see here. So angle AOP is equals to angle BOP. This is you write from the first part. And the third thing, you can see here this side OM. This OM is in this triangle AOP. Also the same side OM is in triangle OBM. So here OM is equals to OM. This is the common side. So hence these two triangles are congruent by SAS congruency. You can see here side, angle, side. So therefore triangle AOM is congruent to triangle BOM by SAS congruency. So whenever two triangles are congruent, their corresponding parts are always equal. So here we can write therefore angle AMO. Angle AMO is equals to angle BMO, and this is by CPCT. Corresponding parts of the congruent triangles are always equal. But in this case we have to prove that this angle M should be right angle. So here if you will see this diagram properly, this AB is the chord, AB is the straight line. So the angle formed on the straight line is always 180. So here I can write that angle AMO plus angle BMO, the sum of the angles should be 180. You write here straight line angle, because the angle formed on the straight line is always 180. But this will be your equation 2, you can assume. This is equation 2. So since from equation 2 angle AMO is equals to angle BMO, you can see here angle AMO and angle BMO are equal. So I can write here twice of angle AMO is equals to 180. This is from the equation 2. Since both the angles are equal, clear. So here I can easily write twice of angle AMO is equals to 180. So therefore angle AMO is equals to 180 by 2, that is 90 degree. So we got that angle AMO is 90 degree. So therefore OP is the perpendicular bisector write the same statement. OP is the perpendicular bisector of chord AB. So hence proved. This is question number 12. Now moving to question number 13. In the given figure, two circles touch each other externally at a point P. AB is the direct common tangent of these circles. Prove that tangent at point P bisect AB. So in this case, you need to prove that tangent at point P. So first of all, you will draw a tangent passing through the point P. This is the tangent. So this tangent bisects the side AB. Suppose this point is M. So you have to prove that AM is equals to MB. Bisect means dividing the side into two equal parts. This is the only thing you have to prove here. So let's start proving. So again in this case you have to apply this theorem 2, that tangents passing through an external point are always equal. So in this case, if you see this figure properly, this is the circle and here M is the exterior point. So here AM and MP are the tangents. So I can write here AM is equals to MP. Since the reason you write from theorem. Because here M is the exterior point and the tangents passing through an exterior point are always equal. In the similar way, since M is the exterior point and MB and MP are the two tangents, this is equation 1. So again I can write here MB is equals to MP. This is again from the same theorem. And this will be your equation 2. Now if you compare equation 1 and equation 2, compare 1 and 2, you will see the right hand side, this is MP, both are same. So both the things will be cancelled out. So you will get AM is equals to MB. So since this AM is equals to MB, so hence we can say that tangent at the point P bisect the side AB. So therefore tangent at point P bisect the side AB. So hence proved. Now moving to question number 14. Tangents AP and AQ are drawn to a circle with center O from an exterior point A. Prove that angle PAQ, so this is PAQ, is equals to twice of angle OPQ. So here this is OPQ, this angle. So here first of all write what you have to prove. So in this case you have to prove that angle PAQ is equals to twice of angle OPQ. So let's start proving this. So here in this figure I can write that angle POQ plus angle PAQ is equals to 180. This is from the theorem. I told you that the sum of the central angle and the exterior angle is always supplementary, because in this case this is the radius, OP is the radius and PA is the tangent. This angle will be right angle. In the similar way, OQ is the radius and AQ is the tangent. So again angle Q will be 90 degree. So now these two angles are left, angle O and angle A. So therefore angle O plus angle A sum will be always 180. You can write here from theorem. And this will be your equation 1. Now in triangle POQ. So now in triangle POQ, since OP and OQ are the radius, so therefore we can write OP is equals to OQ, equal radius, or we can write same radius. So here if the sides are equal, here OP is equals to OQ, so therefore we can write that angle OPQ is equals to angle OQP. And here the reason will be the angles opposite to the equal sides are always equal. Angles opposite to equal sides are always equal. So here we got that this angle OPQ is equals to angle OQP. Now if I apply the angle sum property in the same triangle POQ, so by angle sum property, angle OPQ plus angle OQP plus angle POQ, their sum will be always 180 degree. This is the angle sum property. So just now we got that angle OPQ is equals to angle OQP. This is angle OPQ and this is angle OQP. So as both the angles are equal, so can I write that twice of angle OPQ. Since both the angles are equal, so hence I can write twice of angle OPQ, and this is plus angle POQ is equals to 180, and this is your equation 2. So now if you will compare equation 1 and equation 2, you will see this RHS part, this is 180, this is also 180, so both are same. So simply equate this LHS part. So here by comparing equation 1 and equation 2, so if you compare equation 1 and equation 2, you will get angle PAQ plus angle POQ is equals to twice of angle OPQ plus angle POQ. So now if you will compare both the sides, this is angle POQ and this is also angle POQ. So both the angles cancel out. So hence you got angle PAQ is equals to twice of angle OPQ. This is the only thing you have to prove. So here hence proved. So this is question number 14. So please have a look. Students, I hope you all understood all these sums. Now the rest sums I will solve in my next video. So till then, stay connected and do not forget to like and subscribe my channel. Thank you.